Exciting class today, as always. It's exciting for me personally because you get to do most of the work while I get to chat with the fellow faculty members. Okay. So, what are we going to do today, right? We are into the last stretch of the course. This is the last unit, branch and bound algorithms. Okay. We briefly touched upon it just to give you a glimpse as to what is coming this week, right? I'll lay down the concept, and these are the applications of branch and bound algorithms. Okay. Today's focus would be on traveling salesperson. Remember we looked at TSP in different nuances in this course. So how do we apply branch and bound techniques to TSP? That is the only focus for today's class. Okay. You will get to do a lot of hands-on in terms of writing stuff on a piece of paper, okay, as a group exercise. Less emphasis on the lecture, more emphasis on actually doing it. The reason why I choose this approach for this section, every class we do, by now you already know, I don't let the student just simply sit there and listen, right? You get to participate, you get to do exercises. Here it will be a little bit more involved exercise as opposed to short 10-15 minute exercises. What I will make you do is one big exercise. Slightly different because I personally think that it's not an easy topic to understand by just listening to a lecture. I might even screw up the lecture later on. There's no guarantee that I make you understand it. Remember one or two scenarios where we said it's much harder to explain rather than doing it to get an idea, right? This falls under that category. So I will lay down the concept that goes totally. A 45-minute lecture. Maybe a little longer, shorter. I have not done. Followed by almost an equal amount of time as a group exercise. And the group exercise, the faculty members have to coordinate that. Because it's a longer exercise, right? I make sure no answers given, nothing put in the chat unless I in private mode. Depending on the question. Okay. SPCW there. Couple of them are missing today. So hopefully I'm falling sick. Chakravarti, later we need to Friday night I'll take my daughter to a Kung Fu lesson between 8:30 and 11 p.m. here, so 10:30 or so. In my time it would be around 12:30 p.m. your time. Something like that would work out better. But we can discuss that while the students are doing the exercise. Okay, let's jump into it. Make sure you all have a lot of paper, pencils or pen. My voice is breaking. Can you hear me now?
లేదు సార్ బ్రాంచ్ అండ్ బౌండ్ టెక్నిక్ చెప్పింది
ఓకే ఇంపార్టెంట్ చెప్పడం
we'll see how it goes. I may have to. If it becomes worse, I'll probably reboot my laptop and come back. Okay. Because I have to things over here. Let me close it. Okay, I have good morning. We are in good shape. Now, look at the call. Look at the applications as I meant they jump into the knapsack problem, but my intention is not to do knapsack today. I just want to focus solely on travel. Load the slide deck and print it in a hand notes type format. It will come in handy for the students today when they do the group exercise. Okay, so as we briefly discussed last class, towards the end, it is basically a variation of backtracking. Okay, I would say whether you call it variation or it's a improvement over backtracking, because basically what you're doing is instead of building the entire tree for the problem by using the concept of a bound, we are pruning the tree. That means the state space that you have to traverse is reduced. So that in a sense means the time it takes to come up with a solution is reduced. Okay? We use it for optimization problems. One of the examples that I gave you is the capitalization problems, if you recall. I can actually use a branch and bound there to do that. There is a problem called resource scheduling. You can use branch and bound for resource scheduling. Things like that. Okay? So the theory says that whenever you're building that state space tree, right, you're putting a bound on the value of the objective function. Okay? Whatever the objective function is, right? In the case of resource scheduling, resources and people scheduling, when I want to hire people for certain jobs, as a businessman, my objective function is to minimize my cost, right? If Harry, if I should use some Indian names, if Uma can do a job in for $10 or 10 rupees, and if Pratap can do it for 5 rupees, same time, same quality, then I would choose the guy with the lower cost. So that is my optimization function. So for every problem, there is an optimization function. Okay? In the case of traveling salesman problem, the optimization is obviously we want to take the shortest route possible. Right? In the case of knapsack, the optimization function is what? The total value of the thing that we put in an AppStack, right? The value should be the highest. Okay. So within the context of a state space tree and an optimization function, we use the concept of bound, where we rule out certain nodes as non-promising. Non-promising means we can determine that those nodes, it would not lead to a better solution, better than what the bound is. So we eliminate them from our traversal. Okay, so that's what the essence of branch and bound is. Okay. We briefly touched upon this slide last time when I was wrapping up. So similarities, they both use the tree concept, the state space tree concept. We have done a lot of examples on that by now. You are familiar with that. Okay. Now, in the case of backtracking, if you notice, we always did a depth first search. There is a specific way we traverse the tree, that's the depth first. In the case of branch and bound, you no longer have that limit. Instead of going depth first, you actually can go breadth first. We'll see how that looks like in TSP problem. Okay? And then as a rhythm is best first order. Okay. That means now we expand B. Which are the things that we have left? B, D, and E. And then in this case, of course, the to E. Now he expands that to the next level. So he's going to do the same thing. From E, he's going to calculate for all these other nodes. Okay, recursively. Remember, it's a tree and we are using a recursive algorithm. So it comes with these numbers here, because remember, in order to do this, you need to know the distance from each node to the other node. Remember, paired table. You need that. Okay. So you expand this to each of these nodes. Okay, that's step number 5.
Sure.
Now, as you are expanding, he is keeping track of the live node list. Okay, and then he's adding to the list. So all the nodes that are considering, you're adding that to the list. Okay, so that list keeps growing. Okay, so the order of our live node list, you can convince of how these things came here, right? So you have C2, B1, B2, D. The way of maintaining that one. And then you prune. How do you prune it? As long as the values are less than candidate thing, you keep it. Otherwise, you'll what do? Now you choose the next again, best candidate first, right? Once you choose the best candidate first, you can see you're expanding node G here somewhere. Yeah, node G. So you continue along those paths, and when you continue along those paths, you can see the steps that you go through to exhaust the full tree there. Okay, I'm skipping the gory explanation there because unless you do it, you would not appreciate it. You will be literally doing this, all these steps now. Okay, it's the same thing again. The concept is the same. Now, once you do that, what do you see in the final picture? Here is right. If you look at the lowest value that you see at the end of it, got it? since there is nothing here which is lower than 28, whatever candidate tour that we have chosen to begin with, it so happens that it's also a minimal tour. Got it? There could be many minimum tours, okay? But our goal is to find just one minimum tour, right? Based on our objective function. So we found the minimum tour based on how we did the tree expansion and pruning of the tree when the minimum value is greater than the candidate value. Okay? So that is the branch and bound algorithm there. Now there's another example which I'll just introduce you to, but I want you to work on it yourself, the students. Okay. In the previous case, what happened was we lucked out. The candidate tour that we chose also turned out to be minimum 2. Okay. Now, how often will we be so lucky? We won't be that lucky, right? Here is an example. Shows they chose another candidate tour. Remember, choosing a candidate tour is almost like it's almost bordering on arbitrariness. Almost. It depends on from which city you start, right? So here is another initial tour that we planned, which is the length of 32. Okay. And then calculate stroke. Okay. On that you have the same algorithm, and then once you go through that process, same thing. There's absolutely no difference between what we have done in the previous set of slides and these slides. Okay. Candidate tour. Okay. So you can, but mute yourself, please. Somebody, 1 second, mute yourself. 1 second. Will you mute yourself? I don't know who that is. Okay. SWCW. Okay. I think it will. Jntuk K49, and they are now muted. Okay. So, what story here? Story is most of it could be from any city. Apply some greedy heuristic. You create first level tree after you pick the candidate tour, right? And then you start applying the heuristic of the bound. Okay. And I showed you how to calculate that bound based on the matrix. Okay. Start pruning the tree where the values are greater than the bound that we have. Now, remaining set of promising nodes. Remember in the beginning, the promising nodes. So within the promising node, choose the best value. Because we are saying, hey, we'll always choose the best value. This is the lowest value. Okay, once you choose the lowest value, then and repeat the same algorithm again. Okay, so you can go through that. You probably go through 3, 4, 5 lakhs deep or something like that, and then ultimately you get to either the candidate one that you selected is the shortest, or you will discover what is the shortest. And when do you stop it? You stop it once per node. Always that. Somebody might ask me how many iterations we do it. You do it till you cover all the nodes. Okay. Let me pause here for a second. Questions, comments before I make you do a big group exercise here, which could take substantial time. Okay, so what is the exercise here? let me explain the exercise. Okay. So I'm giving you a graph, A, B, C, D, E. Okay. Not A, B, C, D, E, F, G, H. It's a slightly small form. So you can select any starting point. Faculty members or this is what I would like you to do. If you have 5 groups, let the 5 groups choose A, B, D, E. It should be such that all point. Okay. I'm estimating this exercise would probably consume the rest of the time with a 5-minute break in between. Okay. If it is sooner, great. If it is not, it's okay. Now you determine a candidate tour. Mandatory, you could use some other method, but a greedy method really allows you to come to the okay, then you will define a bounding heuristic. Till you arrive at the solution. What is that solution is nothing but we are going to compare your solutions. We are just going to put it in the chat for all of us to see. Okay. Somebody asked a question. Jntuk. What if 2 don't get equal cost? Which path we have to choose? But it's a type, right? Or one arbitrarily. Okay. Students, let me see. I want the videos to be on, as you know. This is a fun exercise. Groups of 3. I want meticulously written assignment. This is almost like an assignment, right? I want these trees. You should be able to explain the trees. If you pick a group of students to explain what they have come up with, we might do that if you finish it. It's fun. You will learn a lot by doing this particular exercise. Students, you have any? Okay, sounds good to me. Then let's get going. Turn on your videos. I can see that. Okay. How do you do this? Right. The slides are posted. So please, as I mentioned at the beginning of the class, please print out the slide deck in a handout mode or something like that. Each group can take one handout and follow the slides. Okay. In the meantime, I'll just put just this one in case you have already memorized the slides. This is the exercise. This is you may want to copy that on a sheet of paper. Okay. Time now academic 11:40 అయింది అనుకుంటా కదా. Somebody asked a question there. I have to look up, Andy. I did not pay attention to the live notes there. We can work on it, and I can figure that out. If some other faculty member figures it out, please put that in the answer here. While the students are doing it, we'll also do it. Okay? If the video is on, you can see the videos, and please print out. It's a fun exercise. Faculty members, make sure every group does it by choosing a different starter node. Jntuk, I will 49. Jntuk dot 49. I don't know what dot 49 is. Are they all doing it? You can unmute yourself. I can hear all the fantastic interaction and all that. If you are interacting, I don't see any videos today yet. Perfect. So students are able to print out the document. You need the document or the slide deck, I mean. Again, faculty must ensure every group is actively participating. This is not goof off on my students. Every student should do it. This is a legitimate final exam question, by the way. I have the faculty members to assign different starting points to different groups. Okay. Say that's a 1 minute. It's a 1 minute thing, right? Remember I said you can apply the greedy algorithm to choose the candidate. Let me see, I'm seeing Jntuk Kakinada. Jntuk Kakinada with the yellow shirt right in the front. What is the candidate tour that your group chose? What was the starting point? You can say the starting point. And then the two. So what is the starting point you chose? Jntuk Kakinada they choose. Okay. By using these examples, A as starting point, right? So you got the A as starting point, and the tour was A, C, D, D, E, A. A, C, D, B, E, C, D, B, E, C, sorry, E, C, E, D. E, C, E, D. So that kind of gave you the tour as 1 plus 2, 3 plus 3, 6 plus 7, 13 plus 8, 16. Okay, that is Jntuk Kakinada. You want to put something in the chat? What was your starting point? I hope somebody has a starting point other than A. Whichever group did a starting point other than A, put it in the chat for me, please. Come on, it shouldn't take this long because we have been working at it for 40 minutes, 30 to 35 minutes, or maybe a little bit longer. Okay, I cannot wait. So I will go to SVCW. SVCW, tell me what starting point you took. Any group. The question I'm asking is to SVCW. What is the starting point you chose? D. Okay, let me put there D. Perfect. And what is your tool? What was the tool that one of your groups came up with? Whoever chose the starting point D. If you can type fast, that will be great, because I wanted to cover a couple of things before we wrap it up. Okay, if any other group has something, they can put it in. Okay, A, B, C, D, E. From Jntuk Kakinada, your turn is already over. You already answered. Okay. SVCW. What about the other groups here? Let me see. Pragati, Mandava. Please feel free to type. Point that you did, right? You didn't take 35 minutes to figure out a starting point and candidate tool. That's a 3 to 4 minute exercise, right? So, okay, let me go with the first one here. So when you did whoever told me the first one there, let me go back here. We said, so for CT1, so we got a starting point, right? So when you did the tree there, so what are your results? Was it easy to do it? I'm assuming it's easy to do it because it's a fully connected network, right? Now define a bounding heuristic. So what did you get the bound? What did you get? What was your bound? Is the bound basically the 16 there? Or was it something else? Is that one? Second thing is, did you find a tool which was better than that? Last one. Better than any candidate. So if you can answer that, that would be great. How come we did not put any answer yet today? And SVCW. Almost all of you are super active. Today no one put the solution there yet. Other than Jntuk Kakinada. There should be some competition here. Come on. Okay. So Jntuk Kakinada, what was the? Did you find it tool? Come that far yet, applying those steps.
Yeah, అది కూడా అంటారు మీకు ఎందుకులేండి డైరెక్ట్గా క్లాస్లో మాట్లాడేది.
Looks like you probably have not completed all the steps. That is the only logical reason I can think of for you to be quiet, right? By the way, it's perfectly okay to say that, hey, we didn't complete it yet. Okay. Great. So, but I hope, what I hope that you will do is, if you have not completed, if I were you, the same group, you better sit down during your lunch break or something. Would be helpful to you for the final exam point. I can tell you that. Let me take some questions now. I had some solution. Let me see if I can put up how the tree looks like, right? Let me open up the file here and then I can show it.
సార్ స్ట్రీమింగ్ డేటా యాక్సెస్ మరి హడూప్లోకి వెళ్ళాలి.
The top, I did not verify it. I couldn't figure out how the lower bound 14 came there. But if I redo it, I mean, you know how to compute the lower bound, right? Based on the example, you can do that. But if you draw the tree somewhere here, as you can see, you started off with some candidate tool, and then at the bottommost here, you can see when you did that, you can see how you were able to discover an optimum tool, better tool, first tool, because the candidate was 24. I think this lower bound was really 24. I think it could have been a typo there. You can see how you can figure out some. A nice branch and bound, you can way of doing it. Gives you better time complexities compared to the standard backtracking technique. What else is there? As such, the traveling salesman problem and NP heart problem, right? So these are all said and done. This is the best that you can do. This kind of reminds me of something like testing. In the computer science world, when we talk about testing, can you ever say after you finish testing that your program works 100% correctly? That's why they probably would or would not have touched that. See, you can never be 100% sure that your code works after doing even 1 month of testing. Because testing is pretty much an NP-hard problem. You simply do the best guess that you can. You either run out of budget or you run out of time, and then you stop and say testing is complete and it is working. Now, in theory, you can never complete it, right? That is the reason why, even though when you test it, you say put QA signs off saying it works. When the product so that is the reason why we always look for some suboptimal solutions. It's like good enough, right? As long as it's good enough for what I'm doing, I'm happy. So that these problems fall under that class. Okay. Questions, comments? How many of you have done at least 50% of what I asked you to do in the class today? Are you at 50%, 25%, 75%, 90%? That feedback in the class today. Before we meet, I would like some of you who are motivated to send me your solution, okay, for the exercise that we did in the class. Whoever sends me that solution, I'm going to discuss that in our next class, And those students, whichever group that I will make sure that you get some nice meals for lunch. Okay? The expense is on me. Okay, next week, knapsack, that is the next one. To give you a heads up again, the last week we are meeting 3 Saturday, following Saturday. Following Saturday is 12th. So, we are doing it on 19th. Okay, no problem. So the week of 14th we have 3 classes, 14th, 16th and 19th. Right? And then I'm going to be using those, I'm hoping that I would finish the couple of other things in this section by next week. We have 2 more classes next week, right? I should be able to wrap it up or maybe use part of 14 to do it. And then we would have reviewed all 6 chapters again, or all 6 units. Okay, check out the copies from this final exam.
సరే నేనేం మాట్లాడను, నేను ట్రావెలింగ్ సేల్స్మెన్ ప్రాబ్లం ఏంటి?
What did you say?
You need the previous model papers out of
Correct. Any previous final exam papers on there, that would be helpful, right? For the students as well as from a review perspective.
I'll mail you.
Okay. Can you put it in the community or they are supposed to be top secret?